In this video, I'm going to lay out the theory of higher order linear differential equations. That is, equations like this one, which is the fourth derivative of y plus some coefficient function x squared times the third derivative of y plus e to the x y is equal to 3, just as an example. And what my real goal is to lay a solid theoretical foundation here for the methods to solve these types of differential equations. So the general equation I'm talking about here, a general linear higher order differential equation, is as follows. It's some expression like this. What you have is, well, first of all, you have the dependent variable y and its derivatives. And this is going to be an nth order differential equation because its highest derivative is n. That's y to the bracket n means the nth order derivative. We're going to assume that they're linear. And that just means that we're adding up these functions, but with coefficient functions out the front. My standard labeling here is to put a 1 in front of the nth derivative, but then in front of the n minus 1th derivative, I call it the coefficient function p sub n minus 1. And all the way down to y, which is sort of like the 0th derivative, I put the coefficient function p sub 0. And then on the far right-hand side, I have this f of x. And if this f of x was 0, that's going to be important to our theory a little bit later. We give it the buzzword homogeneous. Now, a lot of the theory in the nth order case is really going to be going in parallel to the theory that I've already talked about in the second order case. All right, so let me state my first theorem that's relevant for such differential equations. This is my existence and uniqueness theorem, the key thing that makes differential equations work. It says this is when there exists a solution, and even better, when that solution is unique. So the context here is I start with an initial value problem, an IVP. An initial value problem consists of a differential equation. So here I'm assuming a linear differential equation together with initial conditions. Now this is the first spot where things change. Because this was an nth order differential equation, highest derivative was n, I need to have n initial conditions as well. So you'll notice I have b0 up to bn minus 1, 0 up to n minus 1, that's n different conditions. So for example, if it's second order, you need 2 initial conditions. If it's 10th order, you need 10 initial conditions. Then, provided everything is nice, like the coefficient functions, the pi and the f are continuous on some interval, then the existence and uniqueness theorem guarantees that yes, there exists a solution, and that solution is unique on the entire interval where your coefficient functions and your f are nice. So we have this pretty strong existence and uniqueness theorem that's true for higher order linear differential equations like this one. And indeed, other than jumping up to n initial conditions and nth order differential equation, this is really the same thing that we've seen now 3 times. We saw it in the first order, we saw it in the second order, and we saw it now in the nth order. The next point is one that we've also seen back when we were talking about second order. It's the principle of superposition. And this is the idea. Imagine you have n solutions to an nth order, and this is important, homogeneous differential equation. Homogeneous meaning the right-hand side was equal to 0, as I've highlighted in pink. Then the idea is this. If you found n solutions, you could take any linear combination of those, c1y1 up to cnyn, any linear combination that you wish, and that also solves the differential equation. The basic idea is that since my equation is linear, and derivatives are linear operators, then this all just plays really well with taking a linear combination. Everything works together. So you find any solutions, linear combinations of them are also solutions. This is extremely powerful because if you didn't have a theorem like this, you could go and find one solution, you could find 2 solutions, you could find 100 solutions, and you'd be like, okay, great, you found 100, but there could be infinitely many. How do you find all the others? Well, this is going to get us a long way to being able to rapidly expand all the solutions that we can find. But this still isn't quite enough. Because if you've gone and found n solutions, and then using this principle, what you get is sort of n infinite families, like the linear combinations of those n, you still don't know that you found them all. Maybe there's more. By the way, it's good to keep clear the difference between what we're talking about now and existence and uniqueness. For existence and uniqueness, you had initial conditions, so there was only one. Here, I haven't specified initial conditions, so I'm trying to solve the general solution to the ODE without initial conditions. We could do initial conditions from this at the end. Okay, so now we get to the most important piece. And it's the following. I call it the general solution theorem. And it says the following. Suppose you have n solutions to this nth order linear differential equation. Then my claim is that this is enough. This is enough to describe every possible solution provided some statement about the Wronskian. That is, The linear combination C1y1 down to Cn is the general solution. General solution means any solution can be written in this way. And that is true if and only if the Wronskian of the y1 down to the yn is non-zero at some point t0. So this is really good because it now tells you when you can stop searching for new solutions to your differential equation. If you find n of them, and you find that those n solutions you've gotten are linearly independent, this is this test we have with this Wronskian. So if you find that you have n linearly independent solutions, that's it. Every other solution can be written in this way. And that means you're done. You solved your differential equation. If you had n initial conditions as well, you could substitute in and figure out the values of the constants. Now, for those of you that know a little bit of linear algebra, I want to make the analogy a little bit stronger. We have this wonderful theorem in linear algebra that says, suppose you have n linearly independent vectors. Well, if you live in n dimensions, then the linearly independent vectors form a basis, which means any vector could be written in terms of those n linearly independent vectors. Well, it's sort of really the same type of statement. We're imagining that we're living in n dimensions because we've got an nth order differential equation. And if you have n linearly independent solutions, then the linear algebra word would be to call them a basis because anything could be written as a linear combination of them. In differential equations, we typically call these not a basis, we call them a fundamental set. So y1 down to yn is called a fundamental set. And this means, well, precisely what we've written down here, that there's linearly independent and that any solution can be written as a linear combination of them. So this gives us the following method. If I'm trying to solve an nth order differential equation, what I do is first, I need to find n solutions to that nth order differential equation. Then I need to check that indeed those n solutions are linearly independent, which we have a test for. You take the Wronskian, you see whether it's non-zero at some point in the relevant intervals. And then if you have that, you're done. You can just go to the general solution immediately. It's the linear combinations of the y1 down to the yn. That's your general solution. Now, we've actually been using some of these ideas implicitly already in what we've done. So let's just go back and review and make sure we're doing the same thing. So for example, in the case of constant coefficient ODEs, which is an example of a linear differential equation, then we had this method of figuring out, well, guess y equal to e to the rt. You got a characteristic equation, you solved that equation, and you got two different roots, and finally, you plugged in and got your general solution. We've done this before, that's why I went quickly. But I just want to note how compatible this is with our theory. What we're saying here is that for a second order, in this case, differential equation, you got two different solutions, e to the 3t and e to the minus 2t. Those two solutions are linearly independent. You could check if you wish that their Wronskian would be non-zero. And then indeed, the general solution is all linear combinations of those two fundamental solutions. And we've seen there's some cases, like if there were repeated roots, you'd have a different pair of linear independent solutions. If they were a complex pair of roots, you'd have a new way to express this. And we saw how to generalize this to higher dimensions. We've done all that before in our exploration of constant coefficient ODEs. And the point is just to say, yes, all that we did before is just compatible with this theory. Our theory basically says this is why that method that I introduced earlier works.